All right, how's it going, guys? So we're picking up from graphing speed or motion to velocities. This is lesson 2.4. This is on velocity. It's not much more. I'm not going to add much more onto last lesson. I'm just going to mostly explain the differences between speed and velocity. So we looked at scalar measurements and then vector measurements. Remember that speed was scalar. It only implies direction. So it only applies magnitude. How large is the speed, right? The magnitude of the speed. Is it a large magnitude, small magnitude, medium magnitude, whatever. And that's a scalar measurement, right? But whenever we have velocity takes into account the direction in which something's traveling. And this is why we often use graphs to represent velocities of objects, because velocities naturally, having direction, have to have positive and negative values. And what makes it easy to represent them on graphs is that the y-axis has positive and negative values. So you could decide which direction is positive, which direction is negative, and therefore, depending upon the trajectory of the object, you can decide where to mark that on the y-axis. So remember, velocity contains direction, and it's the change in position over time. Remember, displacement, which is the real numerator for velocity, is defined as a change in position. How does your position change over time? That is displacement. So in the case of velocity, its y-axis is going to be position. It's going to be measured in some form of distance, but it's a position. And the time axis is going to be just like always, like seconds, minutes, hours, that kind of thing. So it's time on the x. Velocity can be both positive and negative, and it just depends on which direction the object is traveling. So the slope of a position time graph is the velocity. So just like the slope of a distance time graph, right, was the speed, velocity is the same thing, except it's the slope of the position time graph. How does the position change over time? You'll see on this first graph that the position does not change. In this graph, the position is the same at the starting time as it is on the ending time. That means it had a zero velocity. It did not change its position. Therefore, velocity must be zero. However, in this case, the position did change. It changed in a positive direction. It went from here to here over the course of time. And it did so exponentially, just like we looked at the distance time graph where you had an upward curve. This is an upward curve on a velocity graph. So this is a little different. This is changing its position in a more positive direction, and it's increasing its velocity over time. So as this was increasing speed, right, and acceleration, it's increasing the speed. This is increasing its velocity. Same sort of thing, just a little different in the terms of either vector or scalar measurement. So if we look at these different examples of velocity on position time graphs, we could see that right here the slope is zero. That means velocity is zero. And the slope of the graph, whether it's position time or distance time, tells you its derivative. In the case of position time, we're talking about velocity, whereas distance time is speed. So in this case, you have a very linear graph. Therefore, this is a constant positive velocity because it is moving in a positive direction up the y-axis. Over here, it's moving in a negative direction down the y-axis. This is a negative slope, like this is a positive slope. So in a negative slope, this is where it's a little different than a distance time graph. You can't have a negative slope on a distance time graph. You can have a negative slope on a position time graph because velocity can be negative. So in this case, you moved in a more negative direction. Therefore, the velocity is constant, but it is negative. So a linear graph, this one's moving in a positive direction. It's a positive slope, which means its velocity is positive. This one is moving in a negative direction, which means the slope is negative. It's constant, but it's negative. You have a curve here, similar as before. The slope means that the curve is not constant because it's upward curve. If you cut this into pieces, you would see that the slope is different in different points. However, it is positive because it's going in a positive direction. If we were doing a distance time graph, we would not even bother to associate this as a positive change in distance because it's just distance. But because you see the position here, you need to make sure you understand that that's positive position displacement. It's moving in a more positive direction. So this is what they would look like if they were translated to a velocity time graph. Just like before when we translated them to speed time graphs, we're looking at a velocity time graph translation. So you're taking the slope here and you're plotting it over time on the velocity time graph. The velocity was 0, there it is. Velocity, which is on the y-axis, is 0, and it stays at 0 because this is a constant change or it's a constant position. It's not changing its position. In this case, it's changing its position. Constant, positive direction, so this is going to be a positive constant value for velocity. Negative constant value for velocity for a negative slope or a negative change in position. This is an exponential change in position, meaning it's an upward curve. It's changing its position more rapidly. It's increasing its velocity. Therefore, it is increasing its velocity. You guys can see how these things change. So we're translating these graphs to these graphs. This graph will decide what this one looks like. This graph will decide what this one looks like. We do this a lot. We change the graphs a lot. Okay, you might get a question that prompts you to tell me what a velocity time graph would look like given the position time graph seen above or something like that. You might get a question like that. So you have to be able to change the graph type. You must be able to take the slope that you see on this graph, and not with numbers, but just with a given figure, maybe multiple choice of multiple different figures. You have to be able to decide which one represents which. Same thing on a story graph. We had a story graph for speed. Same thing, story graph for velocity. So here you go. We have an accelerating object. Velocity is accelerating, right? This is an object where its velocity is increasing. This would be the upward curve on a position time graph. And then it accelerates even more quickly. And then it has a steady speed. This is a constant linear graph on a position time graph. Then it's going to slow down. Rapid deceleration. This is the downward curve on a position time graph. It's stopped. 0 velocity. It's not moving. Speeds up in the opposite direction. And this is how it can get on the other side. This is going in the opposite direction, right? So pay attention to where it lies on the y-axis. So I want you to think in your brain and come up with some ways that speed and velocity are the same, some ways they're different, okay? You've probably done these Venn diagrams before. I don't need you to actually draw it on a piece of paper, but if you want to, it might help. Think about the ways they're the same. Think about some ways that they're different. Think about if you were given the same video with an object traveling and you were to take control or take part in plotting its motion on 2 separate graphs, one a speed graph, one a velocity graph. How would those graphs be different? Ask yourself that. Okay, guys, that's all I got for you today. We'll pick up on acceleration tomorrow.